All right. You're in the right session if you're here for hearing how you could use a satisfiability solver to not exactly play better pickleball, but to schedule a pickleball tournament in a fairer way. So, long time ago, this man told me that the Boolean satisfiability problem was NP-complete. So I was going to do an audience poll here, but there's not a lot of people. But before I tell you who he is, or formally define what the Boolean satisfiability problem is, or even tell you what NP-complete is, I'm going to ask the audience, who agrees with him? Who thinks that the Boolean satisfiability problem is NP-complete? So raise your hand if you think that is true. And we've got one person who thinks it's true, and we've got somebody who does not think it's true. So we'll find out by the end of this. So who is he? He is Professor Peter Poole, who taught me as a first-year undergraduate in 1980 in Computer Science 101, which, in retrospect, this was kind of an advanced topic for Computer Science 101, but the fact that he told me that in 1980 and I remember it now probably means he was a better computer science professor than what I thought he was at the time. But I still remember it now. But let's go over the reasons why he might have said that. And the first one, for all you Toronto natives, which we'll get to on the next slide, is the Cook-Levin theorem. The other thing about proving that Boolean satisfiability is an NP-hard problem is that it's a very useful problem for proving other problems are also NP-hard and therefore NP-complete. And we'll get to the definition of NP-complete in a minute. And then why teach this to a bunch of first years who in 1980 had probably, like myself, had never seen a computer before, and you're throwing them in the deep end here with some advanced computer science theory. This is something that I learned from my kids once they went to college, that there is such a thing as a weed-out class, and they definitely did not have the facilities for everybody who was currently in first year to do the practical classes in second year, so they had to get rid of some of them. So I think he was trying to scare some of us off. So this picture of Professor Poole is from 1985, so that's pretty much how I remember him, because he was my professor in 1980. So, Cook-Levin theory. I think it's misnamed. Stephen Cook, the University of Toronto. He's still at the University of Toronto, I believe, Professor Emeritus. This is how you did papers in 1971, which is when he came up with this. This was done on a typewriter, and this was advanced typewriter because it's in 2 columns. So you've got to, I passed year 10 typing by not being able to type, but by being able to very quickly determine how many spaces you had to leave to get a string centered. So that got me through year 10 typing. So this is what they were doing in 1971 when you were publishing a paper, is that you were typing it up, leaving spaces so you could add your special characters later. And this was a landmark computer science paper and ended up earning him the Turing Award. And what this paper does is it does 2 things. It shows that the Boolean satisfiability problem is in fact NP-hard, and 2, that it's mappable in polynomial time to any other problem that is NP-hard. So if you wanted to prove, it's quite hard, and I'm not going to go through it now, but it's quite involved to prove that something is NP-hard. I have some intuition around that I'll share with you later, But the actual formal proof, like most formal proofs, is hard. So if you have a problem that has been proven to be NP hard, and you have some new problem that you can map to that original problem, then you've proven that that other problem is NP hard as well. And that's much easier to do than proving everything from scratch. So it's called the Cook-Levin theorem. Stephen Cook came up with it initially in 1971. Levin, I can't remember his first name. He's a Russian, so I probably can't pronounce it. He discovered it independently in 1973, so they're naming it the Cook-Levin theorem. To me, it's the Cook theorem. Okay, what is a constraint satisfaction? What is a Boolean satisfiability problem, which is a subset of the more general constraint satisfaction problem? And I'm contractually obligated to mention AI. This is the one hidden reference to artificial intelligence in this talk. This definition is the one that everybody uses, and it's in this book called Artificial Intelligence, A Modern Approach. I looked at the 4th edition, which is the most current edition. And a lot of people use this. So that's the only time I'm going to mention AI, other than to say that constraint satisfaction and Boolean satisfiability problems, the solution to them is useful to AI for verifying models. So it's not as though you use AI to solve these problems. These problems are helping you verify that what AI is producing is correct. So we're done with AI. Okay, so a constraint satisfaction problem consists of 3 things. A set of variables, a domain for each variable, and for Boolean satisfiability, the domain for each variable is obviously just true and false. So that's what makes a Boolean satisfiability problem a subset of a constraint satisfaction problem. It's just a reduced domain. Whereas if your variables are integers, which we're going to see later, then the domain is obviously a lot larger than just true or false. And then finally, you have a set of constraints specified on those variables. So it's reducing the allowable range of the domain for each variable. And that's the formal definition of a constraint satisfaction problem and a Boolean satisfiability problem. So, NP-complete. Complexity raises as we move up this graph. You start out with all of the problems that are in the set P. P is things that can be solved in polynomial time. That's what the P stands for. NP, it's strange. What it actually stands for is non-deterministic polynomial time. So something that can be solved in polynomial time, you can think of in an abstract, in your imagination, you can think of a Turing machine, and a Turing machine has got an infinite paper tape and a print head, and it can move things back and forth, and it can print things, and it can erase things, and you can have logical steps that eventually will produce the solution to your problem on this paper tape on your Turing machine. A non-deterministic Turing machine is something that I think is a little hard to imagine, because anytime you hear non-deterministic, that means guessing. So that means that your Turing machine can jump around on the tape and put things anywhere, and it might guess the solution to your problem. It will if you let it run for an infinite amount of time. And you can verify that the solution that it gave you is correct in polynomial time. So that's what NP means. It's I've asked this question when I've been interviewing people. What is NP? Explain NP to me. And one solution one answer to that question that I really liked in an interview is one candidate said that P was things can be solved in polynomial time. NP is not polynomial, which is not strictly correct. The acronyms line up, but you can see P is a subset of NP. And then you have all of the problems that are harder than NP. Well, they're not harder than NP. They're NP hard, but they may not be NP complete. And that's what Stephen Cook proved in his 1971 paper, was that every problem that is in NP complete is mappable to every other problem that's in NP complete. So saying that Boolean satisfiability is NP complete or constraint satisfaction is NP complete is very handy, because that means that any other problem that you can say, oh, that kind of looks like a constraint satisfaction problem, then and I can map it to a constraint satisfaction problem, which is a very general problem, as you saw, then you can prove that it is NP complete as well. So, as a working programmer, I took this to mean that if I encounter a problem that I've been asked to solve, or I'm trying to solve a problem as a subproblem and it's NP complete, I shouldn't bother, because it's not solvable in the general case in a reasonable amount of time. So to me, the practical implications of something being NP complete is this is not something that a computer can solve efficiently. It's going to take too long. So don't write the code to solve Boolean satisfiability. Even if that's part of the problem you're trying to solve, you've got to find some other way to get around it, because it's just going to take too long. And that's all based on what Professor Poole told me in 1980, and for over 40 years, that was sufficient for me. That's I lived my life that way, and it never came up as an issue. So then I was at a meetup of I'm work in New York City. There's a very, very active Meetup community in New York City. I try to restrict myself to only going to one Meetup a week, but it would be very easy to go to more than one a week, because there's so many interesting Meetups. This was at a Meetup in, you see the date there, September 29th, 2023. PWL, Papers We Love. So this is a Meetup where people, for a long time, it was Papers We Love written by Leslie Lamport, because it seemed as though every paper that that somebody presented there was a Leslie Lamport paper about distributed systems or synchronizing clocks, or there's a lot of interesting problems. He wrote a lot of interesting papers. People love to talk about them. That's what Papers We Love came about. Nathan Taylor, who is also, he was from the University of Toronto at the time. I believe he's moved to Austin more recently. He was giving a presentation on a paper that he wrote, which was kind of unusual for Papers We Love, but he came down from Toronto to present this in New York. And so it was definitely an interesting paper, an interesting presentation that he gave on liquid type systems, which was to do with, at a higher level of some things that you can prove about programs by checking the types. And I've got a clip here of Nathan's presentation, and I just wanted to play you. It's only about 20 seconds, so I just wanted to play this for you.
SAT is the Boolean satisfiability problem. It asks something the following. Any code I show you here is from the Z3 SAT and SMT solver library, which is great. Like anytime you want to build tools that use satisfiability, Z3 is a great choice for it.
So, mind-blowing for me, who's 43 years before this said Boolean satisfiability problems Next, that one's, can't do that one, I'll work on the next one. And he's saying in this type checking system that he's developing, part of it was a Boolean satisfiability problem. He was doing this in Python, import Z3, he called it Z3. In New York, he should have said Z3. And he could just define variables and say, this is a Boolean variable A, this is a Boolean variable B, this is the formula or the constraint that I'm trying to solve. Not only would it say, is it solvable or not, which is what Cook said was NP-complete, the fact whether it was solvable, it produced a solution. This was mind-blowing for me, that there's this whole universe of solvers out there. He talked about the Z3 solver, which is from Microsoft, and we'll see later on where that actually came from. But this is now solvable. It's based on that talk and that realization that there were these solvers for Boolean satisfiability that are usable, I thought, does P equal NP now? Does NP, can I solve all these NP-complete problems? Is that, have I been wrong for 43 years? And so I looked at, I did a bit of research, came across these two books. They're actually part of volume 4 of The Art of Computer Programming. The first 3 volumes have been published. Donald Knuth is working on volume 4. He releases different parts of this as what he calls fascicles. I'm not sure how you pronounce that, but they're subsets of volume 4. So he writes different chapters, different sections, and releases them separately because he wants to get feedback, he wants to get reviews. And also he's doing this very slowly, so he wants to get stuff out there. So Fascicle 6 came out in 2018. It's more about satisfiability as a whole, not just Boolean satisfiability. And so he started out with Boolean satisfiability there, and then this one, which came out in 2025, is the more general part of constraint satisfaction. And if you're going to write a book about satisfaction, is there a better quote you could start with than that one? It's, that hooks you right there. So this is too much text. I couldn't edit it because it's a screenshot. I just wanted to bring your attention to the last sentence of paragraph 1. You'll see that satisfiability is a natural progenitor of every NP-complete problem. So nothing has changed. Boolean satisfiability is still NP-complete. It's just that some practical solutions to the problem have since emerged because so many people are working on it. It's such a useful problem to solve. So, how would you solve a Boolean satisfiability problem? So, this is where my intuition comes in. That if you have a Boolean satisfiability problem that is A and B, under what conditions is that true? And you can think, well, A could be true or false, B could be true or false, combining them together. So you've got 4 options. You've got 2 variables and 4 options. You add a variable to it, so A and B and C, now you've got 8 options. So it's going up exponentially. And that's what makes it NP hard, is that it's not a polynomial factor of the size of the problem. The problem goes up exponentially as you add variables. So that's my intuition about it, which I think still holds, is still true. So how do you solve it more quickly than doing an exhaustive search and enumerating all of the 2 to the n possibilities for all of the different variables. Well, if you think about it as a tree, and so you're trying to solve A and B and C. Well, first you pick a value for A. A could be either true or false. And so you go down the true side. And so you build up, okay, now you've got B, and you pick, B could be true or false. And if you enumerate that entire tree, then that's the same as doing the exhaustive search. But because you're treating it as a tree problem, you can be a bit smarter about it. And the technique that they use it is called backtracking. And in the A and B and C problem case, that's a bit too simple. In more complicated cases, you can get down to a node in the tree and say, this is never going to be satisfied. This particular node, there's no point searching any further in the tree underneath this node because this node itself is never going to be true. So you can skip that entire subtree and jump back up to where you made the decision where that node got into an unsatisfiable state. And there's backtracking, where you just go back one level, and then there's this other thing called back jumping, which is jumping back even further, a little using some smarter rules. And so by doing that, you're reducing the size of the exhaustive search by eliminating things that don't matter. There's also, there have been a number, this is a very active research area, there have been heuristics for looking at, you've come down to this node, you've got to pick another variable that you're going to include in your solution next. There are heuristics that you can use that will pick a variable that will get you to an unsatisfiable state quicker so you can eliminate more of it. This third point it's kind of a shorthand. It's if you get to a point that you know is not satisfiable, you can add that as a clause. So typically a satisfiability problem is a bunch of variables ANDed together and then an OR and another clause of a bunch of variables ANDed together. So if you get to a spot where you know it's not satisfiable, you can add that or the negation of that clause to your problem, and that will prevent you from searching under that any further at any other point. There's also some very efficient indexed data structures you can use to keep track of all this. So the combination of these, that's what Knuth takes 320 pages in volume 7, or fascicle 7 of volume 4 of Art of Computer Programming. He describes these in a lot more detail. It's really mind-blowing. Okay, so as I said, there's a very active meetup culture in New York City, and one of the most active meetups is Rust Meetup. And so a couple of years after Nathan's talk in 2023, I was at a Rust NYC meetup given by Paul Butler. Unfortunately, there's not a video clip. There was the recording for this is not online yet, so I can't show you a clip of it. But when Nathan used the Z3 solver to solve Boolean satisfiability problems, Paul used this thing called SCIP, which I have the what the acronym stands for. I think it's solving constraint integer problems. It's a model that happens to be a Rust implementation. It's not really a Rust implementation. There's a crate that you can install in Rust, but it actually calls out to a C library. Same with Python. You can do the same thing in Python. There's SCIP. And it lets you set up a constraint satisfaction problem. More general than a Boolean satisfiability problem. You can use integers, you can use floats, you can use Booleans, and you can set up the problem that way, and it will produce solutions for you. When this recording comes online, I thought this was a very good presentation, and it was a very interesting problem that he was solving. And that there's this international postcard exchange, and these are computer-generated postcards. So basically, these people, I'm not sure if there's rules to it or not, but they come up with these incredibly intricate computer-generated designs that they print on postcards and they send to each other. And so he had a bunch of constraints. He was the organizer of this. And it was, it's huge. There's hundreds of people in this. And he had all of these constraints on who would send a postcard to who. So obviously, you don't send a postcard to yourself. Not only do no participants send more cards than they signed up for, every participant, if you send 3 cards to 3 random people, you're going to get 3 cards back from 3 different people. You're not swapping cards. So he's got these lists of hundreds of names, and he's got to arrange it so that everybody who sends 3 cards gets 3 cards back from 3 different people. And if you send a card to this person, you're not allowed to receive a card from the same person. So very interesting constraints. And, you know, if you had 6 people, it would be pretty easy to do. But if you have 600, and people want to send different amounts. Like some people want to send 3, some people want to send 30. And so he was trying to maximize the number of cards sent so that everybody who wanted to send 30 could send 30. There'd be 30 people who would send to them, another 30 people who would send back to them. And the reason I recommend this talk, 1, the cards that they're sending are incredible. They're really amazing. And 2, the way that he solves it and the way that he displays his solutions is these 2x2 grids of this person, you know, at the intersection, this person sending to this person, and then a very good talk. And it exposed me to the Rust SCIP crate, which, this is another example from his talk of where constraint satisfaction. There's this company called Gurobi, and that's what this company does. They solve constraint satisfaction problems. And if you go to the SCIP website, SCIP is developed by a university in Germany. One of their affiliates is Gurobi. So I think, I don't want to accuse them of anything here, but I think they're just taking the public domain SCIP solver and using it to solve commercial problems and making a lot of money on it. And one of the problems that they're solving is the US NFL schedule. And this is a partial list of the constraints that they had to satisfy in 2019 to come up with an NFL schedule. And, there's, 2 teams must play Thursday of week 14 after playing on Thanksgiving Day. So if you play on Thanksgiving Day, then you don't have to play the following Sunday, you play the following Thursday. And, so they're trying to make it as fair as possible. And this is a video from the Garobi company that describes how they do that. And the mind-blowing thing about this, and we'll see later when we get to my pickleball scheduling, is not every constraint is something that can be expressed mathematically. Sometimes there are political constraints or human-related constraints that nobody wants to write down because they might not be strictly correct or, but they're constraints nonetheless. So the way Garobi does this, it takes them weeks. They have a set of constraints and a set of matchups that are commercially advantageous to the NFL to happen at certain times. Like they always want to have Dallas playing on Thanksgiving because they're a popular team. Lots of people have got the opportunity to tune in and watch football on Thanksgiving, so they want that game scheduled on Thanksgiving. So they have all of these constraints that they can write down and a place to start from of certain games that they're going to have. Doesn't matter, to hell with the constraints. This one's going to happen on this day. And then they take weeks. They just run through and it produces all of these different possibilities. And then they go to all of these stakeholders who have these constraints that they can't write down mathematically. And they say, is this a good schedule? Is this a good schedule? Oh, okay, you don't like that. Okay, we'll take that one off. Here's another one. Is this a good schedule? And it takes weeks. If they could write everything down, they could do it in one run of SCIP. Anyway, that was something that Paul referenced in his talk, and it points to this YouTube video from Garobi. So, this is another place. Once you start seeing constraint satisfaction problems, it's like you buy a Subaru. You don't see any Subarus on the on the road until you buy a Subaru, and then you're driving down the road in your Subaru. Oh, the car in front of me is a Subaru. Oh, that one's a Subaru. You start noticing. Same with constraint satisfaction problems. Once you realize these things are solvable and there are libraries to solve them, you start seeing them everywhere. So there's this newsletter that I read because it's it has some very interesting problems, and it's also written very well in a very entertaining way. And it's written by this guy, Hillel Wayne. It's called Computer Things. And he makes the point that many of the problems that LeetCode considers hard are actually pretty easy if you can express them from a constraint satisfaction library. And the example that he gave is, and you can imagine being given this as part of a computer job interview. Given a set of coin denominations, find the minimum number of coins required to make change for a given number. So an example that he gave, 37 cents, and you're given the US coin denominations. So 25, 10, 5, 1. That makes sense. You get a 25, a 10, and 2 ones. That adds up to 37. So that's pretty easy. But what if so I don't know how many LeetCode problems that you've done, but usually you'll see the description, you'll see the example, you think, oh, this is easy. Take the biggest coin, use as many of them as you possibly can, and then go to the next biggest coin, use as many of them as you possibly can, and then just work your way down. And that makes sense for a somewhat rational coin denomination. That's how they come up with the coins, I would imagine. So that's a greedy algorithm. You take as many of the biggest coins as you can fit into your solution as possible. But what if you've got what Hillel calls a non-well-behaved set of denominations, such as 10, 9, and 1, and you're trying to make 37. So you take a 10. Oh, okay, you take another 10. I can take another. So now I'm at 30. Now I've got to get to 7. I've got to do 7 pennies. But if you're a little smarter about it, you could take 3 9s, then you're at 27, and then you take a 10, now you're at 37. So you're in 4 instead of, what was it, 3, 7, instead of 10. So that's why the greedy algorithm, which is what you might do if you're under time pressure in a job interview, but it's not the optimal solution, and a constraint satisfaction problem, a constraint satisfaction library will get you to the optimal solution. He gives many other examples, and as I say, it's a very entertaining newsletter. I highly recommend it. So, I took his advice. I went to LeetCode, and I selected Rust as the programming language, and I said, use Rust SCIP. Error. So Hillel was speaking very theoretically there. You cannot practically use a constraint satisfaction problem to solve a hard LeetCode problem. I think that's because it would be too easy. So I've mentioned a couple of different, that Boolean satisfiability is a subset of constraint satisfaction problems. So that's that first point. There's another set called satisfiability modulo theories. And so the modulo there is not modulo some number. It's a constraint on the operators that you can use, which has got several real-world programmings. Several real-world applications. So then you have the mixed integer programming, which we'll see an example of, and then answer set programming. I didn't get into that one. That one's okay. So we've seen 2 so far: SCIP from Rust and Z3, which also can be used from Rust. Both of them can also be used from Python. They're really C libraries with foreign function interfaces to be used from other languages. So Z3 or Z3 comes from Microsoft. It's been around since 2012. The reason that they developed it is that they have a system called Daphne that lets you prove things about various, about code. So you can feed it a program and it'll prove things about, prove the correctness of it or otherwise and let you correct it. So that's been around since 2012. The team behind Z3 has won a whole bunch of awards for it, but Z3 was kind of a tool that they needed to produce Daphne. But it's turned out to be useful on its own. So SCIP, I got it right, solving constraint integer programs. It's from, not from a university, the Zeus Institute in Berlin. It's been around for a little longer, and it's a more general library. As we saw, it's the postcard thing couldn't have been solved with a SAT solver. It has to be a constraint satisfaction problem. So, which to use? It's pretty obvious that the SAT solvers, if your problem can be reduced to a Boolean formula of any number of variables, then a SAT solver is going to be the way to go. Because it's more specialized, it's more likely to produce a solution for you. This is the key. Are you looking to say, is there a solution, or what is the best solution? So if it's an optimization problem where you are looking for the best solution, then an SMT solver like SCIP is the way to go. So then there's a whole bunch of other ones too, like this one looks interesting, the Google OR tools, OR for operations research. That looks interesting too, but I didn't have time to. So SMT solvers are very widely used. I've got some examples here. So you've got a set of firewall rules. Firewall rules can be very general. Say allow them for this subnet and disallow them for this subnet, and then you've got another firewall over here, and you want to see this particular IP address. Will it get through both firewalls? That's an SMT problem. Apparently, you can use it to synthesize code from specifications. I couldn't find any examples for that, but the Wikipedia page for SMT solvers claims that that's the thing. Formal verification. That's kind of what Daphne does, but not quite, because it's using Z3. It's not using a constraint satisfaction library. So this is a trick that gets used. What time? Okay, so I gotta get to the pickleball part. Okay, so I'm gonna scoot past this because this is mentioning Daphne. That's how you spell it, not how you might think. Okay, so pickleball. So company I work for, who I don't mention here because this is not something that I've done for my company. This is all things that I play with at home. A pickleball tournament is typically teams of 2. And the easiest way to organize it is single elimination. So you just have a tree, and the winners advance and the losers go home. And the tournament at my work is won by a very deserving pair of players who are younger, faster, stronger, play better as a team than anybody else. They're very deserving winners. And you might have noticed there, I didn't say what year they won, because they've won every year. Every year I've played in the tournament, the same 2 guys have won. So that's one way you could organize a pickleball tournament. Or, and this is something that my son came up with. He organized a pickleball tournament at the place that he works. Perhaps after hearing me complain about losing in the first round to the eventual winners, he chose teams of 3, which kind of feels, pickleball is a doubles game. How can you have a team of 3? Okay. You want to take everybody who wants to play pickleball in the tournament, and you arrange them into groups of 3 so that the average skill rating of each team is as close as possible. That sounds like an optimization problem to me. So the way the tournament works with teams of 3 is that because you have a rating for each player, you can rank the players inside each team of 3. So you have a number 1, a number 2, a number 3 ranked player in each team. And you're playing in pairs. So the first game between 2 teams of 3 is the first and second ranked player on each team play each other. And then the first and third ranked players on each team play a match. And so if one team won both of those, you're done. If it was 1 each, then the second and third players on each team play each other. That's the decider for who's going to win this round. So, how do you rank players? It's a solved problem. There's pickleball associations. This is, I think, from the US Pickleball Association. There's probably a Canadian one. It's self-assessed. You say where you are here, and then you look up what your rating is. I think they should define it better. Consistent serves and returns. Yes, if you serve a fast serve to my feet, I will consistently hit it out of bounds. So yes, I am consistent, so that does not make me a 3. I'm a 2.5. So. Okay, so that's one of the things that has got to happen before my son's system will work. So when he described this to me, I asked him how he arranged the teams, and he said he just had all the names, all of the rankings, and it wasn't that many players, so he could just arrange them himself. And I said, what if you have 99 players? And he goes, well, we didn't. So he could just do it by himself. But I thought, now this sounds like an interesting problem. Let's try and use SCIP to schedule this hypothetical pickleball tournament. So what this is doing, it's defining a function that takes a set of IDs, so that's the names of the players, and a set of rankings. So every player has a ranking. And I made my life easier by saying you've got to have a number of players that's divisible by 3. And the number of groups that you're going to end up with is the number of players divided by 3. We need the total score, and yeah, okay, so there's some targets. So this is where you, Rust SCIP, you've got to define a model, and then we're going to add variables and constraints and domains to that model. So, okay, so up until now, I've pretty much been listening to smart people at talks and reading books that smart people have written. This is what I did. So, I came up with a 2-dimensional array of Boolean variables. So here, this is adding a variable to the model, and it's a binary variable, so it's an integer. SCIP is for solving integer problems, so I couldn't add it as a Boolean, so I added 0 or 1. And so there are, it's a 2-dimensional array. So on one axis is the number of groups, and across the top is the number of players. So this is how you add a model. You've got to say what the minimum value is, what the maximum value. Then there's this thing about weights. What's the importance of this variable? Not relevant here, so I made it the same for everything. So then I wanted to know, I wanted another variable, but this one was a continuous variable, whereas the previous one was binary. Binary. So I needed a variable to track the deviation in the skill level between groups. And that's what I'm going to optimize, is minimizing that. So using my 2-dimensional array from 2 slides ago, I could add the constraints. So each player has got to be in exactly one group. So that's by, so this is this coefficients thing. I made them all 1, but you need a coefficient. So this is saying go through all of the players and add a constraint to say that you're in exactly one group. So that was easy to do based on that initial 2-dimensional array that I set up. And then this is the next constraint. Every group has got to have exactly 3 players. They're kind of complementary constraints here, but it's just adding another constraint saying it's got to be 3. This field, you may have noticed that in all the variables and all the constraints, for some reason it wants a name. So, and the names have got to be unique. So I just use the group number as the name. And previously I used the player number as the name. So these are the constraints that are minimizing the variance. So it's got the deviation on the upside and on the low side. So you've got the average of all groups, and then you've got the average for this group, and you want the deviation on the low side and the high side to be minimized. And so you just tell the library to solve it. And then once it's solved, you get the status, and then all the information of who's in what group is in the status. Okay, and this is just the main function where, this is some test data that I tried it on. I have a file that's got a list of names and scores. I read that into 2 vectors, and then I just call that previous function, solve groupings with the IDs and the scores. Okay, so here's the data file. Obviously generated programmatically. They're not real names or initials. They're sequential, so this is just me testing it. And this is the groupings that came. So I did it with 99 players, and we got 33 groups, and it's got you the name of the players in each group and what the sum of all of their skill levels are for each group, and what the deviation is from the average. And you'll see it's not perfect. There was no arrangement of 99 players into 33 groups where the average skill level of all 33 groups was going to be the same. But I wasn't asking for that. I was asking for the difference between the groups to be minimized. And so we end up with 2 groups that have got, this is the total skill level, 2 grous that have a lower skill level than the other. But 31 of them, they came out the same. It's, I think that's pretty good. And then I was interested in the performance of this, so I tried it for different size groups, different size tournaments for total number of players, always divisible by 3. And that's how many seconds it took. And I started out with a multiple of 3, then I doubled it, and then I doubled it, and then I doubled it, and I was trying to come up with a graph. And eventually, when I tried 120, I let it run for a week. It didn't solve it in a week. And this is a 8-core i7. It's it's a C library that's single-threaded, so it doesn't matter that it's 8 cores. It just matters if there's a performance core. But it couldn't solve it in a week, so I think it's not going to get there. So I started backing it off. And I'm always using multiples of 3, and it could solve 108 in relatively short time, but then I let 111 run for more than a day, and it didn't solve it. So 99 is, 100 seconds, a couple of minutes. It could come up with a tournament for 99, but then there's some issue in the SCIP library that is stopping, it's hitting some constraint. And this is weird too. I don't know why that happened, but I did this 10 times, and it came out every time. So there's more to learn by looking at the source code of the SCIP library, but I haven't got to the bottom of that yet. And the code that I wrote and these slides are available at that GitHub repository, and that's the QR code for it. So that's my presentation. Thank you.